Okay. So now we have the volume minimizer, which are special Lagrangians in the homology class. So that's what I described in the beginning of this talk, that we expect that the mean curvature flow, this time Lagrangian mean curvature flow, can be used to study the existence of special Lagrangian submanifolds in calabi-Yau manifolds. Okay, so as always, there will be finite time singularities. So in our scenario, if the ambient space is calabi-Yau, then as in the previous slide, that we can define the Lagrangian angle, and then a surprising thing is that our mean curvature vector, our mean curvature form is actually equal to the derivative of that Lagrangian angle. So so here, although this theta L might be just a multi-valued function, but its derivative is always a well-defined one form, and this time equal to the mean curvature form. So if this angle can be lifted to a single value function, or equivalently, the cohomology class represented by d theta L is 0, then we call this L zero Maslov class. So in this case, the mean curvature vector is actually a kind of gradient flow with the potential theta. Okay. So so here, this equation H equal to J of gradient theta L is essentially equivalent to this mean curvature form equal to d theta L if theta L is zero Maslov, if theta is a single valued function. Okay. Okay, so Andre Nevis showed that if the Lagrangian submanifold starting from a zero Maslov class initial data, then the zero Maslov class condition will be preserved by the mean curvature flow, and more importantly, there will be no type 1 finite time singularities. Therefore, there's no such beautiful self-shrinking behavior in the zero Maslov class Lagrangian mean curvature flow. And therefore, we always have to deal with the more difficult singularities, more difficult type 2 singularities. And as I described in the first few pages, the type 2 singularities are modeled on eternal solutions. And therefore, it is necessary to understand the Lagrangian eternal solutions. Okay, so the simplest example would be curves in R2. And this time the curves are automatically Lagrangian. So actually the curve shortening flow is a Lagrangian mean curvature flow in R2. So in this case, a curve is of zero Maslov class if it is with rotation number 0. So the rotation number is the rotation index of the tangent vector of the curve. So like the figure 8 curve is an example of zero master of Lagrangian in R2. And we've seen that this figure 8 curve develops a type 2 singularity and modeled on the translating soliton, the Grim Reaper. And therefore, the Lagrangian translators actually arise as type 2 singularity models of Lagrangian mean curvature flow. So now we should study the Lagrangian translators. Okay. So now let's F be a Lagrangian translator, and we have seen that these translators are critical points of the F volume. And with the Lagrangian condition, we can say more about this critical point. Okay. So this is a stability theorem for Lagrangian translators. So actually, if we compute the second variation of this F volume in any normal direction C with compact support, then what you will get is a non-negative quantity. So so this tells you that the Lagrangian translators are stable critical points of the F volume. So here, this omega tilde C is just defined as the mean curvature form. And this df star is the formal adjoint of the exterior derivative d, but this time with respect to the F volume, the L2 pairing with respect to the F volume. Okay. So this theorem basically tells you that the Lagrangian translators are sort of local minimum of the F volume. And actually, now we are going to show that they are actually volume minimizers. So F volume minimizers are using a kind of calibrated argument, just like the special Lagrangians. Okay. So now, so by Lagrangian condition, originally the translator equation is a vector equation. And using the Lagrangian condition, we are able to transform this vector equation into a scalar equation. So this is equal to a scalar equation saying that the Lagrangian angle minus the inner product of the precision vector with JT is equal to a constant. Okay, so we may think of this constant as a generalization of the special Lagrangian condition. So in the special Lagrangian condition, we require the Lagrangian angle being a constant. And this time, we're not just look at the Lagrangian angle, but the Lagrangian angle minus inner product of precision vector with the JT. Okay, so recall this function when we define the F volume. So again, we use this function to define another holomorphic M0 form on Cm. So here we just multiply the ordinary holomorphic M0 form dz1 which to dzm with this holomorphic function, non-zero holomorphic function in front of it. So the resulting homomorphic M0 form omega f is not parallel. And therefore, this is not a Calabi-Yau structure. But since it's very close to being Calabi-Yau, it is called almost Calabi-Yau structure of the complex Euclidean space. Okay. So once we get some homomorphic volume form, we can pull it back to the Lagrangian submanifold, and this time it is still like the special Lagrangian case, like the Calabi-Yau case. So this time, the volume is replaced by the F volume, and the phase function become like this. So a Lagrangian translator, that is this being a constant, is equivalent to the condition that if you pull back the real part of this omega f is equal to the volume form, is equal to F volume form. Okay, so this is an analog of the special Lagrangian situation. So it produces a calibrated submanifold in the sense of the F volume. And therefore, by the same argument, we conclude that Lagrangian translators are F volume minimizers. Okay. So let's talk about some examples of Lagrangian translators. The first example is a Green Reaper. So this time is just the ordinary Green Reaper and Cartesian product with the Rn-1. So this is a Lagrangian translator in C to the M, which is the simplest example, I think. The simplest non-trivial example, of course. So so here I subtract the imaginary part of the last coordinate by pi over 2 to make the phase to be equal to 0. So the Green Reaper is asymptotic to a pair of parallel planes P naught union P pi, where P naught is just a real plane in C to the M, and real M plane in C to the M, and P pi is just, you translate it in the imaginary part of the last coordinate by pi. Okay. So we can define a sort of rotated and translated version of the Green Reaper by some angles phi 1 to phi m and some constant lambda. So basically, I rotate the first m-1 coordinates by phi 1 to phi m-1, and I translate the real part of the last coordinate by lambda, and translate the imaginary part of the last coordinate by phi m. Then it is not hard to check that this is still the Lagrangian translator, but this time the phase is equal to the summation of phi j. So this lambda here does not change the phase of a translator. Okay, so this is the picture of the Green Reaper. So basically, you have a Green Reaper curve and cross the Euclidean space, and the asymptotic plane are P naught and P pi. Okay. So here's another example, which is more complicated than the Green Reaper, but they are related. So this time, let's fix the angles phi 1 to phi m So there belongs to 0 to pi, and with summation equal to pi. Okay. So we can define another plane, P phi, in this way. So just rotate the first n-1 coordinate by phi 1 to phi n-1, and translate the imaginary part of the last coordinate by phi m. So this P phi is a Lagrangian translator, trivially, with phase pi. Okay, so if we reverse the orientation of P phi, I would denote it by minus of P phi, then this would be a Lagrangian translator with phase 0. Because the e to the I pi is just equal to -1. So if we change the volume form by -1 to, yeah, so to change the orientation, the volume form become like change sign, then you get phase 0. Okay, so P naught, where P naught is just real M plane C to the M, union P union minus P phi. So this is a union of a pair of non-intersecting planes. So this is a Lagrangian translator with phase 0. All right, so Joyce-Lee and Tsui find a Lagrangian translator, FJLT, asymptotic to this pair of planes. So the picture looks like this. So this P naught is a real plane, and P phi is a rotated and translated version of P naught. And these two planes seems like intersecting along a line, but this is not true, because this is a higher dimensional space that I cannot draw on the paper. So actually, these two planes are non-intersecting. So JLT is a submanifold asymptotic to this pair of planes. Okay. So if we let the angle goes to 0, 0, 0 pi, then these two planes, P naught union P phi, will goes to P naught union P pi. And therefore, no, not so, and then the Joyce-Lee-Tsui translator, FJLT, will actually converge to the Green Reaper. Okay, so the Green Reaper is sort of the limit of a JLT translator. Okay, so now I'm going to describe the construction of the new examples. Okay, so far, the known examples are constructed by making reasonable ansatz and solve the ODE system corresponding to the Lagrangian condition and the translator equation. So, I would like to use the gluing construction to construct essentially infinitely many new examples of Lagrangian translators. So by fusing finitely many Green Reapers. So more precisely, the theorem is the following. So for a dimension m greater than or equal to 3, so then assume we've got n Green Reapers L1 to Ln, with suitable rotations and translations, as what we have done in the examples, and assume they all have phase 0. So assume that the union of these Grim Reapers is connected and pairwise transversely intersecting. Then actually there exists a small delta and a family of smooth embedded Lagrangian translators LT with phase 0, such that this family LT will converge to a union of these Grim Reapers as t goes to 0 in a suitable sense. So we can regard this union of Grim Reapers as a Lagrangian translator with isolated conical singularities. Then this theorem is kind of tell us that the union of Grim Reapers is a boundary point of the moduli space of smooth embedded Lagrangian translators with phase 0. Okay, so let me try to describe the gluing construction. So I will describe just for gluing 2 Grim Reapers, and using and by gluing construction, I would construct a 3-parameter family of Lagrangian translators. Okay, so the building blocks are these 2 Grim Reapers, and there are several parameters. So there are lambda 1, lambda 2 are real numbers, and angle phi 1 to phi m with summation of phi j is equal to pi. Then we define 2 Grim Reapers f lambda 1 naught, f lambda 2 phi as follows. So the f lambda 1 0 is just the ordinary Grim Reaper translated by lambda 1. And f lambda 2 phi is the ordinary Grim Reaper rotate the first n-1 coordinate by phi 1 to phi n-1, and translate the last coordinate by lambda 2 and phi m. Okay, so in this way, we produce 2 Lagrangian translators with phase 0. Okay, so there's a unique intersection point of these 2 Lagrangians. And using the condition that the summation of the angles is equal to pi, we can show that the tangent cone actually satisfies the angle criterion. That is, up to a um rotation and translation in C to the m, this pair of tangent planes can be identified with these 2 standard planes, pi naught union pi phi, where pi naught is the real m plane Cm, and pi phi is the rotation of pi naught by phi 1 to phi m. And with summation of phi I is equal to pi. So there's a sort of unique model to resolve this kind of union of planes, because this union of planes can be regarded as a Lagrangian submanifold with isolated singularity. So there's some smooth model to resolve this singularity. So the model is called the Lawlor neck. So given a pair of transversely intersecting planes P naught union P phi satisfy the angle criterion, then of course the P naught union minus P phi is special Lagrangian, and it is special Lagrangian cone. So the Lawlor neck is just an asymptotically conical special Lagrangian. So it is diffeomorphic to the cylinder as n-1 cross r. and asymptotic to the cone C with some rate. So, so you can just look at the picture. So we've got this union of two planes, and the Lawlor neck is kind of a resolution of this cone. So we can multiply the Lawlor neck by a parameter t, and when t goes to 0, this scaled Lawlor neck will converge to the original asymptotic cone C. And actually, this resolution of this cone is unique. This is proved by Imagi, Joyce, and Oliveira dos Santos. So given any pair of transversely intersecting planes with angle criterion, there's a unique Lawlor neck resolving the isolated singularity. Okay, so the gluing construction goes like the follows. So we just originally we have an intersection point P between these two green reapers. But so since we've got the so these two are just the tangent planes at the intersection point, and we've got the local model to resolve this pair of planes. So so we can replace a small neighborhood around the intersection point P with the scaled Lawlor neck Tn, and then do some identification near the boundary of this neighborhood. And using this, we obtain a smooth embedded Lagrangian submanifold f tilde t, where t is just the scale of the Lawlor neck. And this f tilde t will be called the approximate solution. So this is an approximate solution to the translator equation, in the sense that outside this this yellow gluing region, it is actually a translator because it is just the green reapers. But inside this small region, there are some error terms because the Lawlor neck is just special Lagrangians, not a translator. Okay, but the error should go to 0 once the size of the neck goes to 0. Yeah, for sure, because we are gluing smaller and smaller Lawlor necks inside a smaller and smaller region as t goes to 0. And therefore, for t goes to 0, the approximate solution converges to the original union of green reapers. And therefore, the error should go to 0. Okay, so once we get an approximate solution, we may try to perturb it to become an actual solution. So the perturbation should respect two structure. The first one is it should be Lagrangian. So this is a kind of easier part because the Lagrangian condition is in some sense quite soft. That is, any Lagrangian submanifold which is C1 close to LT tilde can be identified with a graph of a small closed one form in the cotangent bundle. And therefore, we get an infinite dimensional family of Lagrangian submanifolds nearby the approximate solution. However, the perturbation should satisfy the translator equation. And this equation will force the the infinite dimensional family to reduce to a finite dimensional family. Okay. So we actually don't have to. We don't actually have to use complicated methods to solve this nonlinear PDE on the approximate solution. That sounds scary because fortunately we can construct the approximate solution carefully so that the error term goes to 0 as t goes to 0 in a very nice rate. So using that, we can perform the inverse function theorem argument to obtain a nearby solution of the approximate solution. Okay, so after describing the construction, finally, I would like to talk about what is the resulting three-dimensional moduli space of our solution by gluing two Green Reapers. So so we got a three-dimensional family of Lagrangian translators with parameters lambda1, lambda2, and t, where lambda1 and lambda2 controls the translations in the real part of Zm coordinate, and t is the size of the neck. Okay, so when t is equal to 0, this red point represents the union of Green Reapers. So this is just L naught lambda 1 union L phi lambda 2. And we've construct a family, a one parameter family, resolving the singularity, resolving the intersection points between these Green Reapers. So we've got one parameter family here, and each point on this line represent a smooth embedded Lagrangian translators. And as t goes to 0, namely we let the points goes to this red point here, then the translator converge to the singular one, just the union of L1 and L2. Okay, so this is the three-dimensional moduli space of the solution we just constructed. And the same method actually applies to construct more complicated examples. For example, we can construct translating soliton by gluing 4 Green Reapers intersecting at 4 points. So the topology of this thing will be like Sn-1 cross S1 and connected sum with 4 copies of Euclidean spaces. And this solution would have 8-dimensional moduli space. There are 4 parameters controlling the translations of these 4 Green Reapers, and another 4 parameters controlling the neck, the size of the neck in the gluing regions. Okay, so that's all I want to say. Thank you for your attention, and probably see you in the problem session.